Let's look at an example of Stokes' theorem. Let's let S be the portion of the cone z equals 2 minus the square root of x squared plus y squared, where we restrict z to being between 0 and 1. Let's give S the upward orientation, in other words, an orientation that has a positive z coordinate. And let's let F be the vector field y negative x z. I'd like us to verify Stokes' theorem by evaluating both of these integrals. Integrate over c f dot little ds and over s the curl of f dotted with big ds. Now this is going to be a longish problem, so the way I'd like to break it up is in this first video, let's see if we can just figure out what the surface is and also figure out what the boundary curves are along with their orientations. In the next video, we'll calculate one side of this, let's say the right-hand side, and then in the third video, we'll integrate the left-hand side. And these two integrals should come out to be exactly the same. That's what Stokes' theorem guarantees. So to begin with, let's just see if we can figure out what this surface is and how we'll give it a positive, an upward orientation. If we rewrite this a little bit, we can say that z minus 2 is the same as negative the square root of x squared plus y squared. And then squaring both sides, we get that z minus 2 squared is the same as x squared plus y squared. Notice that the minus sign disappears. Now we know that z squared equals x squared plus y squared is a cone around the z-axis. So z equals x squared plus y squared looks like this, where the vertex is at the origin. If I have z minus 2 squared, though, that's going to shift everything up 2 units, so that the vertex is now at 0, 0, 2. So let's put our axes in. Here's the z-axis, here's x, and there's y. Now, let's think about what portion of the cone we're going to have. First of all, notice that if I start walking myself back, when I take square roots of both sides, I would have a plus or a minus. Because of the minus, I'm getting the lower half cone. So I can erase this part. So z equals 2 plus the square root would be the top half, and z equals 2 minus the square root will be the bottom half of the cone. And then further, we're going to restrict the z coordinate to be between 0 and 1. Well, z equals 0 is the xy plane, and z equals 1 will be halfway between there and the vertex. So if I slice this at a height of z equals 1, then I'm further restricting myself to this part of the cone. Next, there's actually a name for a truncated cone like this. It's called the frustum of a cone. Now that we've roughly figured that out, let me redraw the picture a little bit bigger so that we can talk about the boundary curves. So let's capture the important parts. Here's that top circle at a height of 1. Here's the bottom circle, which is in the xy plane. And let me draw my axes in. This is when z equals 1. Down here, this is when z equals 0. So the blue cone is my surface S. And think about how many edges this has. Remember that when I talk about edges, I'm talking about the raw edges from when we cut the overall cone. Well, there are going to be two. There's the one on the top, and there's the one on the bottom. Let's call the one in the xy plane C1. And up here, let's call this curve C2. So C1 is going to be the intersection of the cone with the plane z equals 0, and C2 is going to be the intersection of the cone with the plane z equals 1. Now I said I wanted to give the cone the upward orientation. So if I pick a point on the cone, there are two normal vectors, two unit normal vectors. One of them will point this way, away from the z-axis, and the other one points toward the z-axis. Since the cone is slanted outward like this, then notice that the outward normal is going to have a positive z component. So if the z component is 0, that's horizontal. If the z component is positive, it'll be tilted above horizontal. So the upward orientation is the same as what I was calling the outward orientation before. Now let's think about how we have to orient the boundary curves. If I take the unit normal down here on the curve C1, and I walk around that curve, keeping the surface on my left side, then I need to go from right to left. From left to right. So the correct orientation of C1 is going to be counterclockwise viewed from above. So if I look down on this from above, I need to go counterclockwise around the z-axis. On the other hand, if I draw a normal vector here, and I want to walk around the boundary curve, keeping the surface on my left side, then to be on my left side, I need to go in this direction. And notice that would be clockwise as viewed from above. So if I give you a top view, where we're looking down from the z-axis, then this would be my surface S. C1 would be the outer curve going counterclockwise, and C2 would be the inner curve going clockwise. So now remember, the statement of Stokes' theorem is that the integral along C of f dotted with little ds is equal to the double integral over S of the curl of f dotted with big DS. Calling these guys the left-hand side and the right-hand side. In the next video, I'd like for us to calculate the right-hand side. And then in the third video, we're going to calculate the left-hand side and verify that we get the same answer.